start the recording. Welcome to class for Monday, May 4th, which is, unofficially Star Wars Day, or maybe it's officially Star Wars Day. I'm not sure. We had some good jokes in the chat about, the time derivative of momentum being with you. The other thing, anybody who's ever taken a class from me knows I go on this spiel. So one of my personal pet peeves is that we sometimes use language a little too imprecisely. And one of my least favorite ones is the word ultimate. Because the word ultimate gets used like it means best. It actually doesn't mean best. It means last. Ultimate means last or latest, right? Which is usually where people are using it, right? It's the latest, greatest. But the other fun thing about the word ultimate is that you can do some, because it's based in Latin, you can do some fun things. So for example, our ultimate class is Friday, right? Because that's the last one. And so Wednesday is our penultimate class, which means second to last. And today is our anti-penultimate class, which means our third to last. So welcome to our anti-penultimate class on Star Wars Day, where we're talking about the pendulum. Reminders. Everything's due Friday. That's as clearly as I can put it. Everything is due Friday. The Wiley Plus, I believe, locks you out at midnight Eastern time on Friday. That's when it considers its due dates. So 9 p.m. Friday is the very last it will take anything for the Wiley Plus. Anything submitted to the Google form for the video experiments by midnight on Friday will count. Everything's due Friday. Office hours this week. So Sean has his normal office hours today and Thursday from 11 to 1. I'm also going to have an extra office hour from 11 to noon on Wednesday. So I will stick around after class like I normally do, and then I'll probably take a short break to, stretch my legs and get a drink of water. And then I'll be back on from 11 to noon on Wednesday. The post test, you should take the post test. If you take the post test, or if you complete the post test, I will give you 5 extra credit points on the homework. I sent out a reminder email this morning. I'll send out another reminder email probably on Wednesday and another one on Friday, and I'll just harass you until you get it done. Last thing is the final exam. You need to sign up for the final exam. As of this morning, 17 of you have, which means there are still a few people floating around out there that have not signed up for the final exam. If you are one of them, you should do so. Okay, questions about any of this? All right, let's talk about actual physics. So last time we talked about one type of harmonic oscillator, and that was a mass on a spring. Today we're going to talk about a different type of harmonic oscillator, which is a pendulum. So in your reading, you should have read about the pendulum. If I have a pendulum with a period of oscillation of 2 seconds, and I want to change it so it has a period of oscillation of 1 second, which of these would do that? Dividing the mass by 4, dividing the length by 4, or decrease the amplitude? All right, let me launch the poll. There you go. All right, I'll give you 10 more seconds. Going once, going twice. It's old. All right, so let's look at these. So if you remember, a pendulum, at least for small oscillations, which we'll talk about more later, is a simple harmonic oscillator. So a simple harmonic oscillator, remember, the amplitude doesn't matter. So changing the amplitude won't change the period of the pendulum at all. Just like changing the amplitude on the mass on a spring doesn't change the period, right? Those two things are completely independent of each other. So it's not C. So then the question is it A or B? And it turns out that the correct answer is B, and we'll talk about why here in just a second. So here is the lovely free body diagram of a pendulum from your book. And what we can see here is that there are two forces acting on it. There's a tension force from the string, and there's a gravitational force pulling it straight down. And we know since it's moving along this circular arc, right, it's never accelerating towards the string or away from the string. If we write our coordinate system like it's shown here, where we put our y in the direction of the string and our x perpendicular to that, we get that the tension force is whatever it needs to be to cancel out this guy and also maybe make it swing, right? Maybe make it move in a circle. So we'll come back to that in a minute. But the part that we actually care about, it turns out, is this piece right here, right? That's our force, okay? So our force, if we swing to an angle of theta, is going to be backwards. It's going to be negative mg sine theta, okay? And that's basically just doing trig on the force over here, right? Okay, so if we know the force, we can write Newton's second law. So if we come over here, right, and we know what our force is, right? We just figured that out. Our force is negative mg sine theta in what we called the x-hat direction, right? If you remember, we tilted our coordinate system. So there's y and here's x, right? Well, we can write Newton's second law. Newton's second law says that acceleration is equal to the sum of the forces over the mass, right? And the x component of our acceleration is the one we want to look at first. We only have one force in that direction. It's negative mg sine theta. We divide it by m. And so we get an equation that looks like this. Okay. So this equation, it looks a lot like the one we talked about last time, right? Except for over here we've got x and over here we've got theta. So we have to figure out how to relate these two things. And the way to do it is actually to go back and look at our free body diagram here. So if I switch back over so you can see that. Okay. In our free body diagram, we've got this S, right? S is the arc length. S is how far the pendulum has actually traveled. So if we think about this, right, at this particular moment, X is along S, and actually X will be along S all the time because we're going to keep rotating our coordinate system as we keep swinging the pendulum back and forth. So really, instead of writing this as X, we could write this as S, where S is our arc length, right? So in other words, X is really S. Okay, now what's arc length? What does that mean?
It's like a curved length.
Yeah, it's like the length along the curve, right? And here's the fun thing about using sensible units for our angle. If we use units of radians, right? A radian is 1 radius of arc length, right? So S is just the length of our pendulum times the angle that we're at. So if I put that into here, I get the second derivative with respect to time of the length of our pendulum times our angle, and that's equal to negative g sine of our angle. Now, if we assume our pendulum doesn't change lengths, right, then what we get here is this L comes out, and I get an L second derivative of angle with respect to time equals negative g sine theta. And if I move the L over, I get an equation that looks like this. The second derivative of angle with respect to time is equal to negative g over L times the sine of my angle. Okay, now the symbols are all different, but what does this look like? Remember, we're talking about simple harmonic oscillators here. What was our other simple harmonic oscillator?
Spring.
Yeah, mass on a spring. And the equation for that looked like the second derivative of position with respect to time equals negative k over m times your position, right? So these two look similar, except this business over here, right? This has the sine of an angle. So what do we do with that? So this equation, as it turns out, is not analytically solvable. I don't mean that you don't know how to solve it. I mean, no one knows how to solve it. You cannot write down a function that satisfies this equation, which is kind of crazy, right? It's kind of nuts that I could write down something as simple as a pendulum. I could write down the math for and tell you that that equation has no solution that I can just write on a piece of paper. Now, notice I'm not saying it's not solvable. I'm saying it doesn't have an analytic solution, meaning that I can't write a function that gives me the solution. But what I can do is I can look at what happens if theta is small. In other words, if my pendulum doesn't swing back and forth very far. And it turns out that if theta is small, I can do something here. So how many of you remember what a Taylor series is? What's a Taylor series? All right, I'm getting like a maybe over there. Anybody want to take a shot? Taylor series. A Taylor series is this weird thing that you learned about in calculus, where you said that you could express any function as a polynomial, right? Which is weird because obviously a sine function is not a polynomial. But your math teacher told you that you could express any function as a polynomial. I'm not going to review how to get Taylor series, but it turns out that the Taylor series for sine looks like this. It's theta minus theta squared over 2. Over 2. Nope. I'm getting myself mixed up. Minus theta cubed over 6 plus theta to the 5th over 5 factorial minus theta to the 7th over 7 factorial plus, and you just go on forever. Okay, if theta is small, what happens to each of these terms as we keep going? What happens when you square a small thing or cube a small thing?
0. It turns to 0, right?
Well, it doesn't turn to 0, but if you do a small thing times a small thing, it gets even smaller, right? So if I do 1/10 times 1/10, I get 1/100th. And then I divide it by a number like 6 or 5 factorial, which is, let's see, like 120, or 7 factorial, which is 120 times 6 times 7, which I can't do that in my head. Okay. So what we're going to do is we're going to say, okay, if theta is small, then sine theta is approximately just theta. Okay. And so for small angles, we are going to say that a pendulum follows this equation. Okay. Now, is that correct? No. Is it close? Yes, as long as theta is really small. We'll actually look at this here a little bit. Okay. What that means is that this equation now has the exact same form as this equation. Let's see if I can get them both on the screen. As this equation, right? So our pendulum is the same as a mass on a spring, except for now, gravity plays the same role that the spring constant did, and the length of the pendulum plays the same role that the mass did. Okay? So going back to our question at the beginning, changing the mass, it turns out, doesn't change anything about the pendulum. The only ways to change what a pendulum does are to change gravity or the length of the pendulum. Okay? And for small oscillations, right? So for small, if I just give it a small initial angle, I'm going to get that my angle as a function of time looks like some amplitude times cosine omega t. Okay. How did I guess that? Well, I knew the answer, which is how you solve differential equations. You solve differential equations by knowing the answer. And you think I'm joking, but I'm really not. Okay. So that means now I've got to take 2 derivatives. Well, first let's take 1 derivative. So what's the time derivative of this thing? All right, what's the derivative of cosine?
Negative sine.
Negative sine, right? So the constant just goes right through. I get negative sine omega t. And I have to chain roll the thing because now I've got to take the derivative of the inside. So the derivative of omega times t is just omega, right? And now I just do the derivative again, right? The derivative doesn't care about the a or the negative sign or the omega. And so I get negative a omega times the derivative of sine is
Cosine.
cosine. And I pick up one more omega, which means that my second derivative of that function with respect to time is negative a omega squared cosine omega t. Okay, I want to talk about something here for just a second. So this is weird, and this is something that you're going to have to just wrap your brain around. Before, when we were solving equations, right, back when we were solving good old algebraic equations, the solutions to our equations were numbers, right? If we only had one unknown in an equation, we would solve it, right? And we'd get one value. Or maybe if it was a quadratic, we'd get two values. Now, when we're solving these equations, differential equations, the solutions aren't numbers or single values or two values anymore. The solutions are functions. So congratulations, you've graduated to a new type of math, where when you solve an equation, you get another equation out and you're happy about it. So if we take the second derivative and this value and put them in, right? We just plug them into our equation. So we take this and we put it in right here. And we take this and we put it in right there. We end up with an equation that looks like negative a omega squared cosine omega t equals negative g over L times a cosine omega t. The negative signs cancel, the a's cancel, the cosine omega t's cancel. And so this equation works as long as omega is the square root of g over L. Okay? Cool. So that means that the longer you make a pendulum, right, the more you increase the length, the more you decrease the angular frequency. And decreasing the angular frequency means that your period gets longer, right? So the period of a pendulum goes up when you increase the length of the pendulum. Okay, this also actually has an interesting point to it. So G, right, changes a little bit as you go up in elevation. Not very much, but it does significantly change. So if you are in Chico, G is about 9.81 meters per second. If you move to Laramie, Wyoming, which is at an elevation of about 7,000 feet, G is about 9.78, which means that it actually changes how fast your clock ticks. If you take a big old grandfather clock from Chico to Laramie, Wyoming, it will actually tick slightly slower. I'm sorry, its angular frequency will go down, which means the time between its ticks will get longer. So it will tick slower if you move it to Laramie, Wyoming. Not by a lot, but by a little bit, by a measurable amount. Okay. Now, the solution to this is never move to Laramie, Wyoming, and that'll solve a lot of your problems. But if at some point you do decide to move to Laramie, Wyoming, aside from getting a pair of cowboy boots, you should also seriously check your clocks. Not that any of your clocks actually work on pendulums anymore, but if you have one, you should check it. Okay, so what's the point of all this? Why am I showing you this pendulum? Well, aside from the fact that it shows you another example of a harmonic oscillator, it also shows you something really cool that I want to get back at. And that is this fact that we've gotten to an equation here that we couldn't solve. Not that we didn't know how to solve it, but that it couldn't be solved in the same way, right? If I put a theta in here that has a sine function in it, right? If I take this equation and I plug in the second derivative looks like that and the first derivative looks like that, it won't work, right? Because all that stuff will be inside of a sine function. Okay? So this is not the solution to the pendulum. It's close. It's really close for small angles, but it's not generally the solution. So what can we do? Well, what we can do, it turns out, is we can approximate things. Okay? We can numerically solve our equation. So let's write out our equation here. Our equation was that the second derivative of angle with respect to time equals negative g over L times the sine of our angle. Okay, I'm going to break this up into two different equations. And I'm going to do that by just making one of the equations really dumb. I'm going to define a variable and I'm going to call it Q. And I'm just going to say that Q is my pendulum's angular velocity. I'm not using omega here because we already used omega once today. But oftentimes we would write that as omega, right? So Q is our angular velocity. Okay, which means now I have two equations, right? I have one equation that looks like d theta dt equals Q, and another equation that looks like dq dt equals negative g over L times sine theta. Okay. Now I want you to think back to when you were kids and you took Calc 1 and you learned about derivatives. How did they explain what a derivative was to you? What did they tell you? They said they're introducing this concept of derivatives. How did they introduce it to you? Take a shot, somebody. I promise I won't throw anything at you.
With limits?
Yeah, it's the limit of what?
The limit of a function as it approaches a point.
It's the limit of something about the function as it approaches the point, but what?
So like x minus h thing.
Yeah, it's the slope, right? What they told you was that your derivative, right, is the limit as, you know, your delta t goes to 0 of theta at t plus delta t minus theta at t, and I ran out of space, divided by delta t, right? It's just your slope. So here's what we're going to do. We're actually going to use that. We're going to say, okay, our d theta dt here is approximately just our theta at some future time, right? At t plus delta t minus our theta at the current time divided by our delta t. And we're going to say that that is approximately equal to, or is equal to, our q at some time t. Okay. And now if we solve this for this term, we can say that our theta at in the future, right, at t plus delta t is just equal to theta at time t plus delta t times q at time t. So what that's telling us is that if I know my angle and my angular velocity, I can, and I know how far I want to step in time, I can tell you what's happening in the future. And if I make delta t smaller, this becomes more and more exact, right? In the limit that delta t goes to 0, this is perfect. But I don't care about perfect, right? I only care about good enough, right? I don't need to know the angle down to, 1 part in a trillion, because reality doesn't care, right? I'd never be able to measure that. I'd never be able to have that impact anything. So I'll just make delta t as small as I need to make it. Okay, I have to do the same thing with the other equation. And when I do, the other equation ends up looking like q at t plus delta t equals q at t minus delta t times g over L times sine of theta at time t. Okay. Okay, that stepped me forward one little bit of delta t. But I don't care what the pendulum does one little teeny step
What
in
does
the
that say after sine?
right here.
Yeah.
It's the sine of theta at time t. Sorry, I ran out of the paper a little bit.
Thanks.
Okay, so what does this mean? What this means is now I have a method where I can step one little piece forward in the future if I do a bunch of algebra, right? And if I do, and then if I do it again, I can step again into the future, and again and again and again and again. This is what computers were made for, literally. I literally mean that. This is what computers were invented to do in the first place, is solve these kinds of equations. Because computers are really good at just doing the same thing over and over and over and over again. So let's try it. Let's come over here and let's actually use a computer to do this thing. So let me share my screen again. Oh, hold on one sec. Let me share this. The link is up there, but let me also actually share the link to this. We're going to go to a spreadsheet here. Let me copy the link into the chat. So if you would like to go over there and actually see the thing going, you can. All right. So if I click on this link, it'll take us to a nice spreadsheet, which you can't see yet. So let me switch my screen sharing. Here we go. Okay, so this is just a blank spreadsheet, right? And what I've done is I've made some entries over here, like my time step. So I'm going to step in increments of 10 milliseconds. And I put in a value for G and a value for the length of the pendulum, which means that my omega, my angular frequency, is just the square root of G divided by L. And I hit enter and I find that, oh, look, my angular frequency for this pendulum is 4.427, blah, 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 blah. Okay. All right. First thing I'm going to do, I'm going to move this column over. The first thing we're going to look at is what is the solution if we assume the small angle thing? If we assume that small angle business, then our solution should just look like an initial condition, right? So we have to have an initial angle. let's make it 1/10 of a radian. I should put units on that. Okay. So at time 0, our initial angle should be that, right? But I know what that is. I know what it should be at all of the times. Well, first of all, let me populate all the times. So I'm just going to say that the next time is just the current time plus the time step. And I'm going to do something clever here. I'm going to put dollar signs in front of the G and the 1. If you've played around with spreadsheets much, you know that the dollar sign means keep this reference fixed. And we'll see why that's important here in a second. Okay. So that gives me 0.1 seconds. Now I can do something clever here. I can grab this little box in the corner, click on it, and scroll down. And what it does is it copies the formula. Right? So now originally it said I wanted A2 plus G1. Okay. Next one now is going to do A3 plus G1. It changed, right? It repeated the pattern. But because I had the dollar signs, it didn't do that for the reference to the time step. So, and I can just keep going with this, right? We're going to go down and do 110 time steps, 1 second worth. Okay, now our simple harmonic oscillator, right? We know we have a function that says what it is. So it should just be our amplitude times the cosine of our angular frequency times our time. Okay? And voila, it works. Now, I'm going to go in and put dollar signs in front of the references to column G, because those are the things I don't want to change. I do want it to change the time in there. And if I go ahead and scroll it all the way down, I get a bunch of numbers. And if I plot them, right, if I come over here, and I tell the thing I want, oh, there we go. That actually made kind of a nice thing for me. Great, we'll take it. So there's what happens to my simple harmonic oscillator, right? Let me zoom in just a little bit. It might make it easier for some of you to see. Okay, so cool, right? I've got a nice thing that solves my simple harmonic oscillator problem for me. That's really nice. Okay. And if I wanted it to go for longer, all I would have to do is come down here and just drag both of these further down. You know, so there we go. Now we've gone for 2.09 seconds. And if we come back up here, we're going to have to remake the chart, but that's easy to do. We just go to insert chart and it makes a new one for us, right? And we can customize it and we can label things and we can do whatever we need to do. All right, cool. Let me move this thing. Can I move the thing, please? There we go. Nope. There we go. Put it over here. Okay, so there's our very nice chart, and we feel very happy about it. Now, that's what the answer was if we used our approximation, right? But let's try to figure out what happens if we don't use our approximation. Because we actually figured out how to do this numerically, right? And when we do it numerically, we're solving the actual equation, not the approximate equation. Oh, I just realized, is my video mirrored?
I don't think so.
Like when I'm writing, it doesn't look weird?
Do it again.
So the writing over here is not backwards?
No, it doesn't look like it, no.
Oh, okay. It's just mirrored to me. Whew. I looked at that thing and I thought, man, that is, oh, it's mirrored. So I figured no, and I was surprised nobody'd said anything, but it turns out it's just mirrored to me. Okay, fine. That's fine. All right, so we're going to come back over here and we're going to use this formula that we developed. Okay, so our initial angle again is going to be, well, just the initial angle. And initially we're going to start it off at 0 angular velocity. Okay, so now our next one, we're going to take our angle and we're going to say, okay, it's the previous angle plus my time step times my previous angular velocity. And I'm going to hit enter. And that makes sense, right? Because it wasn't moving. And I'm going to come over here and put $signs in front of the reference to the time step. Now I've got to come over here and update my angular velocity. My angular velocity was just my previous angular velocity minus my delta t times g divided by L times the sine of my previous angle. Okay? And I want to put $signs in front of all the g's, right? All the things that don't change. And I get a number. And interestingly, if I come down here and I drag this all the way down, well, calm down thing. It's going to do something. And now if I come over here and I make a chart that has all of this data, we see something happening here. Okay. What happened?
The red one has a slightly higher amplitude.
Yeah. Look at its amplitude compared to where it started.
It grows.
Yep. Okay. So physics experts out there, what's wrong with this?
That can't happen unless you have a force acting on it the whole time.
Right. We need some kind of, this actually says that it has more energy. All right. It turns out this is based on that approximation we used for the derivative. And if we make the time step smaller, then it will get smaller, but it's still a problem. Now, here's the clever way we can fix that. Okay? If we look in this formula, we used the previous angle and the previous angular velocity in that formula. It turns out that the answer is as simple as using the current. Well, come on, thing. Please. Whoa, it won't let me change it. Weird. Can I just drag it? Nope. Dude, I've never had that happen before. Can I delete it all? Okay, let's try it again. Equals our previous angle plus our time step times, and now I'm not going to use the past angular velocity. I'm going to use the future one, the current one. And I'm going to put some $signs in front of the stuff from column G. And then I'm just going to drag it all the way down. And I find that if I do that, whoa, look at that. Almost exactly the same. Almost exactly, right? It's not quite exactly the same. You can kind of see a little something happening right here. But it's almost exactly the same. And it's not doing that weird thing where it grows in time anymore. All right, congratulations. You have just been introduced to the concept of numerical error. those of you who are engineers will get really familiar with this, because all engineering models that I'm aware of will have these kinds of problems, and you have to do clever things to fix them. And it turns out the fix here is pretty easy. Okay. All right. So now we have some way that works as long as our angle is small. But here's the cool thing. I can make the angle bigger. So instead of 1/10 of a radian, let's start us off at 1 radian. And if I hit enter, now we see something start to change. What happened?
It shifted.
It shifted. The pendulum has a slightly longer period than the simple harmonic oscillator. And it's even going to get weirder than that. Let's make the initial angle. So what would straight up be?
90 degrees, or pi over 2 radian.
So pi over 2 would be straight to the side. So let's give it pi over 2. It turns out there's a pi function. So I can just give it pi over 2. Oh, sorry. It's a function. It needs parentheses after it. And I can even make it, so that's sideways, right? What if I start it straight up? That's pi, right? Now, something interesting is going to happen. If I give it pi, what's it going to do? All right, interpret the graph for me. What does that graph mean?
It's staying in one place.
Yeah, why is it staying in one place?
Is it a slope? Is it representing a slope?
So the slope of what?
Or is it like a rise or a run kind of thing? And at pi there's like no run. It's just flat.
You're right, it is. At pi, it turns out that there is no net force on the pendulum, right? Remember? Because the net force is only the component going sideways. And so if I start this thing perfectly balanced straight up, that pendulum will just sit there. Now, of course, it's not perfectly balanced. Now, nothing ever is perfectly balanced. So let's make it pi minus a small number, right? And now we'll see it do something interesting. What did it do? It'll be easier to see actually if I take this out for longer time periods. Let me scroll down. Right now I'm going out to 2 seconds. I'm going to make it go out, I don't know, a ways. There you go. There's 6.8 seconds. Let's see if that's far enough. Oh, I'm going to have to rebuild my chart. There we go. So what did it do? If I take a pendulum, okay, so now first of all, let me be careful. In this case, it's got to be a rigid pendulum, right? Because if it's a mass on a string, then the ball just falls, right? But as long as this thing is forced to move in a circle, right? What we're saying here is that the real pendulum takes a long time to fall. And then it falls really fast. And then it flips all the way back up, almost vertical again. And then it falls really fast. And then it flips. Does this look anything like a sine function?
Not
It
really.
does. It's just kind of like the peaks are flat.
Right. It is going back and forth, but the shape now has been completely distorted from a sine function, right? A sine function doesn't, it has like peaks. This thing has like bumps, right? They're not peaks really anymore. And so so the point of me showing you this is I want you to see that this small angle approximation gets worse and worse as we get to bigger and bigger angles, which shouldn't surprise anyone, right? In fact, if we actually go to not huge angles, right, half a radian, we're almost right on. Just a little bit of a shift. How big is half a radian? Does anybody know? So the way I always remember it is there are basically 3 radians in 180 degrees. It's actually pi radians, but pi is basically 3, right? So that means 1 radian is about 60 degrees. So half a radian is about 30 degrees. So at an angle of 30 degrees, we're still really close to just being a simple harmonic oscillator. The only thing that's really changed is that our period is a little bit longer than it should be. Okay? And if we make this even smaller, 0.2 radians, now we can't even see the difference. The 2 lines are exactly on top of each other. They're not exactly the same, right? If we come over here and look in the actual numbers, you'll notice that they are slightly different. But now they're different by like 1 part in 1,000 or 1 part in a few hundred, as opposed to being different by, you know, a huge amount. All right, what's my point here? My point here is twofold. One is I want you guys to realize that there are problems that you can only solve on a computer. You can only solve them using numerical methods. And you will run into many of them. I also want you to see a little bit of how you do this. Now, I'm not going to test you on it. I don't expect you to memorize this. But I do want you to see it because you're going to use it a lot. Okay? So, with that, I'm going to stop sharing this thing. And we're going to come back over and do one more example problem here. Okay? So, I started off with this picture of an amusement park ride. Anybody ever done one of these?
Yeah.
They're kind of fun, huh? They swing you back and forth, and then a lot of these actually rotate you around as well. But let's just assume this one swings you back and forth, okay? So you're designing this amusement park ride, and you want it to be basically a large, rigid pendulum. And for safety reasons, you're not allowed to exceed 3 Gs of acceleration on the riders at any time, okay? A healthy person can withstand about 5 Gs, but you know, you're going to have people on this ride that maybe, you know, aren't perfectly healthy, and you really don't want to kill anybody. So you're limited to 3 times normal gravitational acceleration, okay? Your ride is going to be 15 meters tall. What's the maximum angle you can have your ride swing to? Okay? So how are we going to figure this out? Well, the first thing we're going to do is we're going to have to look at this as a pendulum, right? So the first thing we're going to have to do is figure out how to write things with a pendulum. So let me come over here. All right. So if it's a pendulum, right, we know that it's, so here's our pendulum, right? We know that there's a force going this way from tension, and we know that there's a force going this way from gravity, the weight of the object, right? And furthermore, we can break this up into components so that this is going to be weight times cosine, and this one is going to be your weight times sine, okay? We know that this gives you the equation for a pendulum, right? And we know that your angle as a function of time is going to look like some amplitude times cosine omega t. Okay. Now, we want at the end of this something about acceleration. So how do we go from here to acceleration? We've got angle. How do we go from angle to acceleration?
Integrate it twice.
Take the derivative, but you're right. Yeah.
Yeah.
So if we take the derivative of this thing twice, right, that's going to give us our angular acceleration, which, as we just did on the previous sheet of paper, right, just looks like negative a omega squared cosine omega t, right? And we happen to know that a is just our initial angle. And we know that omega squared is g over L, right? Okay, so now we've got our angular acceleration. How do we turn that into an actual linear acceleration? We've got angular acceleration. We want our tangential acceleration. How do we relate the two?
Isn't acceleration equal to angular acceleration times radius?
Yeah, it is. It's the radius, which is the same as the length of our pendulum, right? So it's just the length of our pendulum times alpha, which, if we put all this together, we get that our tangential acceleration is negative a times L times g over L times cosine omega t, right? And if we take this all apart, we get that our tangential acceleration as a function of time is just negative a g cosine omega t. Okay. So what does this seem to tell you? We never want to get more than 3 times our gravitational acceleration on people. And a is our initial angle. So how do we turn, so if we never want this to be bigger than 3g, what does that say about a?
Does it have to be less than 3
Yeah, 3 what?
radians?
3 radians. Now that's huge, right? 3 radians? And it also said that it doesn't matter how big you make the thing. So this seems a little bit fishy. What are we missing here? Which component of acceleration did we just figure out?
Cosine?
Which direction is this acceleration in? Remember, this acceleration was related to this force, right? So that means this acceleration is only your acceleration along the circle, right? This acceleration is the acceleration that goes like this. Okay, it's the component this way. That's our tangential acceleration. What other acceleration do we have to experience if we're going in a circle?
The sign due to gravity, like the up and down.
Yeah, we have to experience some kind of acceleration pointed towards the center of the circle, right? We have to experience a centripetal acceleration too. And we happen to remember, because we're good physics students, that our centripetal acceleration is our speed over the radius of our circle, which is the same thing as our angular velocity squared times the radius of our circle. Oh, now I've done it again. I've used omega twice. Let's not use omega here. Let's call this guy Q. Okay. All right. Well, we know what Q is, right? That's the time. That's the first derivative of our angle. So what's the first derivative of this thing with respect to time? Well, what's the derivative of cosine?
Negative.
Yep, negative sine. And we pick up an omega because we have to take the derivative of the inside. We have to chain rule the thing. So Q is just, as a function of time, is negative a omega sine omega t. Okay, let's plug that in. So that means our centripetal acceleration as a function of time is q squared times r. Remember, r is the length again. So now we've got something that looks like the length times negative a omega sine omega t quantity squared. So our centripetal acceleration looks like negative a L times omega squared. Oh, no, no negative. Sine squared omega t. Now, I can use this again because remember, omega is just g over L. So again, our centripetal acceleration looks like a g times sine squared omega t. So now I've got the two components. How do I figure out the magnitude? Come on, I've got the components of a vector. I want the magnitude of the vector. How do I do it?
You square them, add them together, and take the square root.
That's exactly what I do. So that means the magnitude of my acceleration vector is just the square root of the tangential component squared plus the centripetal component squared, which is a horrible mess, okay? Which is going to look like the square root of my initial angle squared times g squared times the cosine squared of omega t plus a squared g squared times the sine to the fourth of omega t. Well, that's kind of gross, but I can simplify it a little bit. I can pull the a squared and the g squared out and just make this the magnitude of my acceleration is my initial angle times gravity times the square root of cosine squared omega t plus sine to the fourth omega t, which is gross. But here's the cool thing. Basically, what we're saying here is that my a times g is what we're talking about. Now, it's not quite as simple as just saying, oh, okay, what's this thing, right? Because it's a mess. But remember, we're good at messes. We can come over here and plot this thing. So let's plot it. If I open up Desmos, come on, Desmos, there we go. And I share my screen. And I say start graphing. Okay, I want to graph my acceleration on the y-axis. And I want it to be my initial angle, which I'm going to call A times 9.8. Well, actually, I'm just going to call it A because I want the answer in terms of G, right? So I'm just going to say it's A times the square root of cosine. Now I've got to worry about what my omega is, right? So my omega is G over L, so 9.8, is the square root, is the square root of 9.8 divided by 15 meters times t, or times x, that's going to be my x, close parenthesis, squared, plus, and then I'm just going to take this whole mess again and paste it over here, except for now I want it to be sine, and I want it to be to the fourth power. And I'm going to add a slider for A. And voila, there's my acceleration. Okay. And if I make A bigger, we'll see what happens. Okay. I want to make sure it's always less than 3. And it turns out that I can get that this mess never gives me a number less than 1, which means that I get my maximum right there. Okay. So yeah, it turns out if I want to get 3 G's of acceleration, I can tilt this ride almost vertically. And I'll never get more than 3 G's of acceleration on people. Isn't that handy? Okay, how are we feeling?
Good.
All right. What's the point of all this? The point of all this is kind of what we're doing in some sense is gathering in all of these concepts, right? To do this problem, we had to go back and grab centripetal acceleration. We had to grab some rotational concepts. We had to take what we just learned about pendulums. We had to go back and grab vectors, right? We had to grab a lot of different concepts and put them together. This is a synthesis problem. Physics professors love synthesis problems. Okay? You will see them again at some point, I promise. Okay. Everybody feeling okay?
All right.
Yeah.
Slightly fried?
Slightly.
All right. So here's what we're going to do. We're going to call that a class for today. On Wednesday, we're going to do some review. We're going to do review for the whole course on Wednesday and Friday. And I'm going to do it the same way we did last time for the review. I'm going to I'll send out in an email a link to the questions that we're going to be going over on Wednesday. And if you prepare a solution for one of them and share it, present it to the class, I'll give you extra credit points. Okay? So watch for an email. I'll send it out this afternoon. Take a look at the problems, work one of them, come prepared to present it to class, and we'll see how it goes. Worst case scenario, I have to pick at random the order we go in. Best case scenario, it's like last time where you just, everybody gets to pick whichever problem they want. Okay, how we feeling? Busy?
Good.
All right. So watch out for that email. Remember to get cracking on finishing up all the stuff that's due Friday. And I will see you guys on Wednesday.